So before we look at some quadratics, let's look at a linear. So imagine that you're driving down the road at a constant speed of 40 miles per hour. Hopefully you're not on the highway because people are going to be beeping at you. What in that sentence tells me that it's going to be linear? A straight line. What word? Yeah, Zion. Constant, right? So that constant word tells me that I'm going to not change my miles per hour. I'm going to keep going 40 miles per hour the entire time. And there's a table that represents this. So after 1 hour, I went 40 miles. After 2 hours, my total distance was 80 miles. What is the difference between those two distances? 40, correct. After 3 hours, I went 120 miles. What's the difference between those two distances? No, you're good. 40. After 4 hours, I went 160. Well, 40. Yes, those differences are constant. That 40 miles is changing every hour. So if and when I graph this, what kind of graph would I expect it to make? A linear. Oh, surprise. Linear, right? So after 1 hour, I went 40 miles. After 2 hours, 80, 3 hours, 120, 4 hours, 160. Another way to represent this would be an equation. So they use T. We would usually use X and Y. So 40 times however many hours I drove would give me my total number of miles. So this is something we've been doing for like 3-4 weeks. So now let's look at something that would not be linear. So Liam, crazy Liam, is dropping a watermelon from the top of a 300-foot tall building. Because he feels like it, I guess. For YouTube, right? For his TikTok, something. He wanted to know if the watermelon was falling at a constant rate. He films the watermelon's fall and then recorded his observations in the table. So after no time, obviously he's still at the top of the building, which is 300 feet. After 1 second, the watermelon fell, and now the watermelon is at 283.9 feet above the ground. Ooh, what's the difference? Come on.
It's 17.1.
Close.
16.1.
Yes, good. 16.1. I didn't ask you to calculator, but we'll work through it. So if it were at a constant rate, I would expect all of those differences to be 16.1. So let's check the next one. After 2 seconds, we're at 235.6. What's the difference between 283.9 and 235.6? 48.3. Are those the same number? 16.1 and 48.3? They are not. The watermelon's falling faster. In 1 second, it only fell about 16 feet. From 1 to 2 seconds, it fell about 48.3 feet. What about from 2 seconds to 3 seconds? So from 135.6 to 155.1.
Let's just say it's around 80.
That's around 80.5. Good. Yes, decimal addition, subtraction. Good. And then our last fall would be from 3 seconds to 4 seconds. How many feet did it fall? 112.7. I just remember that from last period, I'll be honest. It was gaining distance. Why? Why? Because gravity, right? When you drop something, gravity is going to pull on that thing until it hits something. I don't know if y'all talked about this in science yet, called terminal velocity. Yes, maybe. So when you drop an object, it's going to keep moving faster and faster and faster until it reaches its highest possible speed. Obviously, this watermelon hasn't hit its highest possible speed until what's going to happen?
Teachers and staff, pardon the interruption. Boys soccer practice is canceled today, so players, please make sure we call home and make sure we have a ride. Thank you.
Do y'all need to contact home?
Yeah.
You good? Okay. What's going to happen to this watermelon eventually? Splat. Where's it going to splat? On the ground, right? It's going to splat on the ground. Probably a little after 4 seconds, because after 4 seconds, it's only 42 feet above the ground, right? And then probably soon after that, it's going to hit the ground. So our rate of change, we just said, is not constant. Each time another second went by, more distance passed. So when we were driving our car every hour, I was still only traveling 40 miles. Here, the watermelon traveled 16 feet, then 48 feet, then 80 feet, then 112 feet. So it's going faster every second. And why is that happening? Oh, sorry, Renee.
Isn't it kind of like in the cars, they have like that maximum speed on the
Yeah, speedometer, yeah. I don't necessarily think, do you mean does that have to do with gravity or what?
No, I mean like, because like you said it was,
Oh, like terminal velocity?
yeah.
So that's probably talking like about that physical car can only, like that would be the highest speed that that physical car could go. Different cars have different like
That would be more like
highest
air-
speeds.
Like that would be more like air resistance.
Yeah, like, yeah, you can only make a car go so fast because of like air resistance and
Same thing with the watermelon.
friction from the tires and everything like that. So why is the rate of change not constant? We just talked about that. Because gravity is a thing. Hence why when we shoot the basketball, it doesn't just travel up into the air forever. That would be kind of cool, but it doesn't.
Imagine if it jumps that, you just jump in the middle.
So here's Liam. Liam is up here on this building.
Oh.
And Liam drops his watermelon. It splats, right? We'll get to that question in a second, actually. This is a little bit of review. Independent variable. That is our X values. So what are the units for our X values for this graph? Those are the numbers, the units, like seconds, right? Seconds, time in seconds, good. So our dependent variable would be our Y value. What are the units for our dependent variable? Feet. In the next few weeks, you will get to have all of the knowledge to be able to come up with this equation. But now I'm going to give it to you. Okay. So this is the equation that would make Liam's graph. -16 t squared plus 300. So I'm actually going to show you it in Desmos. Hopefully it'll save in Desmos from last class. We'll see. Oh, look at that. Oh, no. Okay, there we go. So look at Liam's graph on your paper. Look at this graph. Tell me what you notice. It's only a part of it. Your paper is only a part of it. Why would this book only show like this little top right section of Liam's graph instead of showing the entire parabola? That's the name. Graham. Okay, we can't go negative feet. Trust me, as long as if you threw a watermelon very hard against the ground, you're not strong enough to crack the concrete, right? When could we have negative feet? Underwater, yeah. Water is a great way to describe negative feet because usually our ground would be like sea level. So if you drop something like in water, that would be a great way to describe it. Why else? So that would describe not including the bottom part. So not including this bottom part. Why did they not include the left side of the graph? They only included the right-hand side. So Graham said no negative feet, which would be the bottom. Yeah.
instead of it going up.
Up, okay, that's true. Why the left-hand side of the graph though? So here, let me pull back up Liam's graph. So why are we not including this piece of the parabola? Zion? Okay, you're getting there. Madison? You can't have negative seconds, right? Who can time travel? I ask this question all the time. I wouldn't tell anybody, Madison, if you could time travel. Keep that to yourself. Can't have negative seconds, right? So we can only talk about Liam, positive seconds, positive feet. That's why the graph is only showing this. So far, all of these curves that we've looked at have a name. They're called, what's the name, Enrique? No, the other one.
Quadratic.
There you go. Quadratics. Before we talk about the equation though, I want to go back and look at Liam's equation. I don't want you to worry about the negative 16 right now. That deals with the gravity aspect of it, but the 300 is not random. Where in our problem did that 300 come from? He started at 300 feet plus 300. Okay, that's fine. I want you to remember when we talked about linears. Yeah. Yeah, it's the y-intercept. So slope-intercept form, that B was where we started on our y-axis. This constant number is where my parabola touches that y-axis. Yeah. And it might not be the peak. I don't want you to get hung up on that. This one just happens to peak at the y-axis, but it is going to be wherever my parabola crosses the y-axis. So just like we have y equals mx plus b for linear, quadratics have a specific equation. This is what it looks like. Ax squared plus bx plus c. You can write it in that little line. My handwriting's just too large, sorry. So if I am not given a graph, what about that equation would tell me that it makes a curve and not a line? Esteban? The squared, yeah, that squared, the exponent squared tells me in my brain, okay, I'm not dealing with straight lines anymore. I'm dealing with some sort of curve. The A, the B, and the C, for those of you that were able to look at the Desmos, and we'll look at that more on Thursday, the A does something specific to the graph, the B does something specific to the graph, and the C does something specific to the graph. And I promise we'll talk about it on Thursday. What does C do? Yes, yeah, you're right. Good, yes. Yeah, if there's no exponent, if it's just like something x plus c, it would be this form. Right? So we're building from that linear form to make that quadratic form. Okay, here's another parabola. And again, I ruined that again. This shape, its name is parabola. Everybody act shocked.
Oh my God.
Yes.
Oh my God.
Okay. This is the most simple parabola, x squared. It doesn't have plus bx or plus c, its a value is 1. It is the most simple parabola. Where is the minimum, the lowest part of this parabola? At 0, 0, correct, at 0, 0, good. We kind of talked about this already. Why did we only consider the first quadrant for Liam? Because we have no negative time or height. No negative time or height. You, like I said, you could have negative height. It would just depend on if you're throwing the situation, if you're throwing into the ocean or.
Well, I mean, like that'd be actually, right, you know, like, do you know what I mean?
I don't know what you mean.
Like, if we act like there's no, like, ocean counting that's a negative.
Well, I guess you'd have to count the very bottom of the ocean as 0, right?
Right.
Yeah. Yeah, that'd be a little confusing because like the ocean isn't like a consistent
Because of-
depth. Yes, correct. Okay, so we're almost done with Liam, but let's answer a few more questions at Liam. How long did it take for the watermelon to hit the ground? An estimate. Look at it a little bit more closely. So why? Okay, so why would I say like 4.2 versus 4.7, Bryce? It's a little closer to 4. So if we look at his graph, 4.7 is not a bad, at least you know it's between 4 and 5. Okay, well, I guess it was a random good guess then, but I would say closer to 4. So 4.2 works. If you want to be extra, you can say 4.25.
4.24536.
If you want to be super extra, that's fine. But 4.2 is a fine estimate. This is also the x-intercept. It's touching the x-axis at around 4.20. But just like we talked about with, I wouldn't say that I was 0.5 above the ground. Just like I wouldn't say I was 4.2, 0 seconds. I would just say 4.2 seconds. These x-intercepts have a few names. One of those names is a 0. Why do you think it's called a 0? In this case, it's where it ended, right? It's where the watermelon hit the ground.
Because it's worth moving.
That's where it stops moving.
Not for this problem, yes, but not always.
That's where it starts or stops.
For this problem, it's where it stops, so that's not always true. It's called a 0 for every parabola.
It's either the beginning, like, no.
So if we were to actually name this point, it would be 4.2, comma, 0. So it's called a 0 because that's where the y value is equal to 0. So anywhere the y value is equal to 0, that point is called a 0. It's also called the solution. So anytime you hear the word solution, 0, x-intercept, those are all referring to the exact same thing. Wherever that line, curve, parabola touches the x-axis. That would be a good thought to write down. Okay, so Liam, how many times did the watermelon hit the ground? Once. Can you think of a situation where your item would have 2 solutions? So it would touch the ground twice. Yes. Okay, so give me an example of something. Okay, so if I bounced a basketball, it would bounce, it would go up, and then it would go back down and bounce. Correct. So those 2 times that it hits the ground would be 2 solutions. Can you think of anything else? Okay, so for it to make a parabola, it would have to hit the ground to start or once and then come back up and go again. Yes.
I don't have an example, but then would there ever be a point where the parabola is kind of like?
So at that point, it would not be considered a parabola. A parabola is just one change of direction. If it's changing direction multiple times, it's called something different.
Something different?
Yeah, we're not doing that in here. Don't worry. Yes. So actually, like, you're not far off, Zion, but kind of what I was telling Renee, a Ferris wheel, like your distance above the ground is going to change multiple times. Like you're going to be close to the ground, then above the ground, then close to the ground. So it's going to create a different graph than a parabola. So what do you mean? So if you're running, that kind of falls into the category of like the driving at a constant rate, right? If we measured our like distance running, it would probably look more linear than it would a quadratic. Yeah, Graham. Okay, that's a good one. So trampoline. The only thing I hesitate with trampoline is because technically when you're on a trampoline, you're probably not where? On the, You're also not in the spaceship, but you're definitely not on probably not on the ground, right? I'll come back to that though. Keep that thought, because I do have something important to say. I'm going to use a soccer ball as an example. So a soccer ball's on the ground, I run, I kick it in the air. What happens to it? And then what? Then it falls back down on the ground. So I'm going to say kicking a soccer ball. Yeah. So if I were to graph it, this is a very rough sketch. It would look like this. So it starts here on the ground, it goes up, it comes back down and lands on the ground. Wow. Okay, so this is probably the hardest question of the day. Can you think of a situation where your parabola would not touch the x-axis? So I'll draw a picture of what it would look like. It would look like this. All right, Graham. Okay, so in Graham's situation about a trampoline, when you jump down on a trampoline, it goes down. Does it go all the way to the ground? Well, hopefully it doesn't. That doesn't feel like it doesn't sound like that would feel very good. I would say that hopefully it doesn't touch the ground and you spring back up. Jonathan, what do you got?
So like where you jump off of a cliff with the little big kite thing and you fly?
Ooh, you're so close. Jumping off of a cliff, yes, but kite thing, I don't want to use kite because kites hold air, right? And if we're talking about gravity, that kite is going to like stop gravity from affecting you from like falling. So a parabola means that I'm increasing speed and then something happens to kind of bring me back up. Yeah, Bryce.
What about a boomerang?
Okay, what about a boomerang?
Like when it not touch the x-axis?
It wouldn't, but I don't think it would make the specific shape of a parabola. If we're talking about like its distance above the ground,
Yeah, it's still like,
it would just, it would just like a frisbee. It would stay pretty consistent in its distance above the ground because of its shape. Yes.
If something was like maybe like a fall off a tree and the wind picks it up.
Okay, so that's kind of what I was talking about with the kite. So that wind kind of counteracts the gravity effect. So it would not make that like pull down of a parabola and bounce back up. So let me go back to Jonathan real quick. Not a kite, a bungee cord. Yes, bungee cord. So think about that. I've never been bungee jumping, don't have any interest. But if you do go bungee jumping, you start up here, you jump, and then hopefully what happens? Hopefully the bungee pulls you back up and you don't hit the ground, right? So gravity pulls you to that bungee until it's stretched far enough to where it pulls you back up. So it would make that parabola curve. Yes.
If the bungee were to break, you would have a proper, you would have a zero though of the zero
You would have a what?
a zero how do you pronounce that again?
then you wouldn't have a parabola.
Parabola?
Yeah,
What about it?
you would have a zero because if it broke, you would touch the ground, right?
Well, yeah.
So you would have a
Well, you would still technically have a parabola, but I mean like a parabola that's in that shape. That's what I mean. Yes. Okay. So let's look at a few more examples. Oh, sorry, Jonathan, go for it.
What about like in space?
Okay, so what about in space? So it would depend, right? Different parts of space have different gravitational pulls, and we need that like gravity acceleration to make that parabola shape. So I'm not well versed on like other gravities besides our own. So unclear.
Saturn's
Uh-huh.
gravity is
The moon I know is like a sixth of the Earth. So like you would weigh 1/6 of what you weigh now on the moon.
Oh my god, this is so light.
So when we solve quadratics, we always want to look for the x-intercepts. And remember, that's wherever my parabola crosses the x-axis. So let's look at a parabola. So how many times does this parabola cross the x-axis? Twice. So let's identify these two places. There is no word problem. So I would say that you need to call it 2, 0 and 5, 0. And that's because there's no sort of like situation associated with it. 2050. Yeah, Graham.
Can you go back a little bit?
I can. Sorry about that. Oops. Oh, I meant to write bungee jumping here too.
I just didn't know what it was called.
Well, like, I do, like, that's what she said, but then, like.
You're actually the first person out of all 6 of my classes, and I know that's what Graham was gonna say, to come up with that. Good job. Pat yourself on the
What
back.
about skydiving? Wouldn't it be like the?
But the parachute is that same idea where it kind of,
Y'all meant like parachute, right?
No,
Not, like,
I mean,
anything
like,
catching.
wouldn't it create
Like,
the,
are you good, Graham?
Yeah.
Okay.
wouldn't it create the, if you do skydiving, wouldn't it create the one that hits the x-axis kind of parabola?
Yeah, but when your parachute catches, then it wouldn't be a parabola anymore because your parachute is not letting the gravity pull you down.
So if you just jump and don't use it.
And don't use a parachute, then I guess that would create a parabola.
I hope you like.
Bad ending. Okay. So if we look at this graph, Aaron shot a water bottle rocket from the ground. A graph of height over time is shown below. So what type of function is this? So now we have 2 options, linear or quadratic. This would be a quadratic. Agreed.
Quadratic. Agreed. Quadratic.
After how many seconds did the rocket hit the ground? 5 seconds. And that's exact because it is touching 5 exactly there. So this one we're gonna have to estimate a little bit. What is the maximum height of that rocket?
Like 6.1.
6.10.
Sure, I heard 6.1 first. So 6.1 what?
Meters.
Meters.
Come on, guys.
Thank you. Anywhere around 6.1 to 6.3 would be correct. So this point up here has a name. We kind of mentioned it already. It's called the maximum
Maximum minimum.
and minimum. Has another word. Anybody know the other word? It's called a vertex.
Yep, knew that.
Hey, isn't it like the cross? Is that-
Okay, so let's talk about that. So most people are like, well, the vertex is in a shape where like the corner, right? So what vertex means is where it's changing direction. So if you're talking about a rectangle, like my computer, it's changing direction from going up to right here. A parabola changes direction either at the top, the maximum, or at the bottom, the minimum. Both of those are called the vertex though, called the vertex. If you change direction, that piece is called a vertex, correct.
What is it?
Okay, I'm gonna have you answer the beat the test, and then we'll take a break. But I'm gonna give you like 2 or 3 minutes. I do want to go over it before we go on our mask break. So I'll read it. It says, Jordan owns an electronics business. During her first year in the business, she collected data and created the following graph showing the relationship between the selling price and the profit. So the x-axis is her selling price. So she's selling some sort of electronics. And her y-axis is how much dollars she's making profit. So go ahead and try and answer those 4 questions. Okay, so circle the zeros. You should have circled here and here. So want to know something funny? Someone last period, not going to call them out, said that they circled this because those are the zeros. Very funny. Did you do that yesterday, Brianna? Good. I didn't ask you to do this, but if you were to name them, it would be 10-0 and 60-0. So what is that talking about for this problem though? That's what's more important. What's happening at 10-0 and 60-0?
How much money she has in the
Okay, what is the x-axis telling me though? Selling price, okay. She's selling something at $10 and $60. What's happening to her profit at $10 and $60?
No one knows. Oh, wait.
At 10 and at 60. At 10 and at 60, how much money is she making? 0. So at $10 selling and $60 selling, she's making no profit. So let's think about that. When you sell something for $10, seems pretty cheap. Why would you not be making a profit?
Because maybe the thing that you like.
That's how much you bought it for?
Yeah, it could have been how much I bought it for. It could have been how much I made it for. So if I make a shirt for $10 and I sell it for $10, how much money is going in my pocket? Nothing.
You're
Simpkins.
broke.
Or
Okay. So what about $60?
Still.
Why would I not be making a profit when it's $60?
Maybe nobody wants to buy it.
Yeah, and it's too expensive. Nobody wants to buy it. Good. Okay, and then the other question, box the vertex, that's up here. And that was 35, comma, 12,000. What does that represent?
The peak of her career.
Yeah, peak of her, I would say maximum what? Profit. So if you're Jordan, how much would you want to sell your item for? $35, because she's going to make the maximum amount of profit. Last question, then we're going to go take a break. What would happen if Jordan sold her item for $5? She'd get negative, lose money. She'd be paying people to come buy her item. What about if she sold it for $70? She's losing money again, right? Because if we extended that parabola, it would go into the negative profit. Can you have negative profit? Sure. Heck yes, you can. Yes. Lots of businesses end up not making a profit.
Like
'Cause-
clicks.
Sure. Yeah, like a lot of businesses during COVID, lots of restaurants, lots of businesses that weren't like big corporate businesses, did not make profits or made negative profits during COVID.
No